Please pause the video and try this problem. Now let's discuss. We'll start by choosing a problem-solving framework. We notice that this problem mentions the concept of mass, which fits into Newton's second law. It also mentions friction, which is a force, which fits into Newton's second law. The problem also mentions the concept of acceleration, which fits into Newton's second law, and tension, which is a force that fits into Newton's second law. So it looks like we're going to use the Newton second law framework. Now, it is true that the concept of acceleration could also fit into a kinematics framework. But the problem doesn't mention any other concepts that could fit into a kinematics framework. So it looks like we're not going to use kinematics for this problem. We'll just use the Newton second law framework. The first step is to make a sketch of the object and their surroundings. In this case, we were already provided with that sketch. So let's move on to our next step, which is to make a note of what the question is asking us for. This question asked us for the acceleration of the masses and the tension in the rope. Well, to start with the tension, when the professor uses this wording asking for the tension in the rope, what they're probably thinking of is the magnitude of the tension force being exerted by the rope. And a good symbol for the magnitude of that tension force is capital T. Now, what about acceleration? This is a little ambiguous or vague because there are two different masses, which could theoretically have two different accelerations. Also, acceleration is a vector that has both a magnitude and a direction. So the most complete and comprehensive way to interpret this is that the question is asking us for the magnitude and direction of the acceleration of mass 1 and the magnitude and direction of the acceleration of mass 2. If we take that very comprehensive interpretation here, the question is asking us for the direction of the acceleration of mass 1, the direction of the acceleration of mass 2, the magnitude of the acceleration of mass 1, and the magnitude of the acceleration of mass 2. Remember that when we write these symbols without the arrow on top, the symbol stands for magnitude. Now, truth to tell, this probably is a more comprehensive interpretation of the question than what the professor is really going to require. The professor probably is not really going to require us to specify each of these things separately in order to get full credit for this problem. But it can't hurt. It can't hurt to answer comprehensively what each of these concepts turns out to be. So we indicated what the question was asking us for, maybe even a little bit more than what the question is really intended to ask for. And to the extent we could, we represented that with symbols. Now we want to show the object's directions of motion by adding velocity vectors to our sketch. Well, let's see, the problem told us that mass 1 is sliding down the incline and that mass 2 is falling. The direction of the velocity vector indicates the object's direction of motion. We know that mass 1 is sliding down the incline, so velocity 1 points parallel to and down the incline. And we know that mass 2 is falling, so velocity 2 points downwards. Make sure that you label each of these arrows with a specific symbol. Next step, check that the given units are SI units. Well, kilograms are SI units. Those seem to be the only units mentioned in the problem. So, yes, the units were SI units. This step is not relevant for a numeric problem. Free body diagram phase, let's identify the objects we'll be focusing on, usually the objects whose mass was mentioned. The problem mentions the mass of mass 1 and mass 2. So it looks like we're going to be focusing on object 1 and object 2. Those are the objects whose mass was mentioned, and of course those were also the objects that are connected by the rope. What's the interval of time that we will be applying Newton's second law to? Well, we could say that we're going to be applying Newton's second law during the interval of time during which mass 1 is sliding down the incline and mass 2 is falling. Now we start to separate free body diagrams for those two objects. We need a free body diagram to show all the forces being exerted on mass 1. Here's a dot that represents mass 1. And we need a separate free body diagram to show all the forces being exerted on mass 2. Here's a dot that represents mass 2. We begin our free body diagrams by drawing the weight force vectors. The weight force points down. Here's the weight force exerted on object 1 and the weight force exerted on object 2. So we've completed this step by drawing the vectors for the object's weights. To continue the free body diagram, for each object we have to ask what are the things that are touching that object. Let's begin with mass 1. What is touching mass 1? Well, something that's touching mass 1 is the incline. Mass 1 is being touched by the incline, so that can exert a force or forces. Now, the incline is the type of thing that we think of as a surface, which means that it can exert a normal force. The direction of the normal force should be perpendicular to and pointing away from the surface that is touching the object. So the direction of this normal force should be perpendicular to the incline, perpendicular to and away from the 30-degree incline. So we've drawn in this dashed reference line to represent the surface of the incline, and here's the direction of the normal force pointing perpendicular to and away from the surface of that incline. Now we know that any surface that exerts a normal force also has possibly the potential to exert a friction force. And we can see that there is indeed friction in this problem being exerted by the incline. So we have to add the friction force to our free body diagram for mass 1. Are we dealing with static friction or kinetic friction? Well, we know that the mass is sliding down the incline, which means that we're dealing with kinetic friction. The kinetic friction should point parallel to the surface and opposite to the direction that the object is sliding. So kinetic friction here should be parallel to the incline, and the mass 1 is sliding down the incline. So to be opposite to that, the kinetic friction should be pointing parallel to and up the incline. Friction opposes sliding. To oppose the sliding down the incline, kinetic friction has to point parallel to and up the incline. Are there any other forces that are being exerted on mass 1? Well, ask yourself, is there anything else that is touching mass 1 besides the incline? Yes, mass 1 is also being touched by the rope. So the rope will exert a tension force on mass 1. The direction of this tension force points parallel to the rope and away from mass 1. So this tension force is pulling the mass parallel to and down the incline. So here's our symbol for that. Remember that this would not be a good symbol because we need to distinguish between this tension force and the tension force that we're going to add in a moment for mass 2. So distinguish with that this is the tension force for mass 1 with the subscript. Are there any other forces being exerted on mass 1? Well, is there anything else touching mass 1 besides the incline and the rope? No, nothing else is touching mass 1, so there's no other forces we need to add to the free body diagram for mass 1. Now we have to continue the free body diagram for mass 2 by asking, what is touching mass 2? Well, mass 2 is being touched by the rope, so the rope will exert a tension force on mass 2. This tension force points parallel to the rope, pointing away from mass 2. That would be an upward tension force pulling up on mass 2. Again, include the 2 subscript to distinguish this from the tension force on mass 1. Are there any other forces being exerted on mass 2? Well, is there anything else that's touching mass 2 besides the rope? No, nothing else is touching mass 2, so there are no other forces being exerted on mass 2. In particular, mass 2 is not in contact with the type of thing that we would consider a surface, so there is no normal force or frictional force being exerted on mass 2. So we have completed this step. We completed our free body diagrams by drawing the force vectors for each thing that was touching each object. Now we're ready to move on to our force tables. First, we want to choose axes with our positive directions, probably pointing in the object's directions of motion. Mass 1 is moving parallel to and down the incline. So I'm going to choose a positive x direction for mass 1 that is pointing parallel to and down the incline. I've chosen a positive x direction for mass 1, pointing parallel to and down the incline, because that's the direction that mass 1 is moving. And then the conventional choice for the positive y direction when an object is moving on an inclined plane is for the y-axis to be pointing perpendicular to and away from the surface. So that's what I've chosen here. Now for mass 2 is moving straight down. So I'm going to choose a positive y-axis pointing straight down. Mass 2 is moving downwards, so I chose a positive y direction pointing downwards. And then the x component won't be particularly important for mass 2, but for completeness I chose a positive x-axis as well. The most conventional thing when you don't have anything better to do is to choose to the right as your positive x-axis. So since there's no reason not to in this case, I chose to the right as the positive x-axis for mass 2. All right, so notice that we wrote down our axes. We've seen already that you oftentimes can make the problem simpler when you choose axes that point in the object's direction of motion. So in each case, I chose an axis that pointed in each object's direction of motion. And it is okay that we ended up with different axes for the two different objects. It's okay to have different axes for the two objects. By the way, I hope it goes without saying that you always choose two axes that are perpendicular to each other. So notice that in each case we chose axes that were perpendicular to each other. We've completed this step. Now we want to start two force tables for the two objects. Here is the outline of our force tables for mass 1 and for mass 2. Let's start by dealing with the tension forces. We can use this rule. The magnitude of the tension force will be the same at both ends of the rope. That means we can say that the magnitude of the tension force being exerted on object 1 is capital T. And then we can use the same symbol capital T, to stand for the magnitude of the tension force being exerted on mass 2, because the magnitude of the tension force is the same at both ends of the rope. Now, technically, we've seen that this is a rule that applies to a massless rope stretched over a massless, frictionless pulley. The problem did tell us that the pulley is massless and frictionless. The problem did not specifically say that the rope was massless, but that doesn't really make much difference because we've mentioned that for an introductory physics course, we're generally going to assume that the rope is massless unless the problem indicates otherwise. Otherwise, there would be no way to get an answer to this problem. So we'll assume that the rope is indeed massless, and therefore we can say the tension force is equal in magnitude at both ends of the rope. Now we break these tension forces into components. T sub 1x, well, this tension force is pointing in our positive x direction. So it will be positive, and it'll have magnitude capital T, and the other component will be 0. Notice how we write down the plus or minus sign first, and then we write down the magnitude. Now for mass 2, tension force 2 is pointing upwards, which is our negative y direction for mass 2. So T sub 2y will be negative. Write down the negative sign before you write down the magnitude, or you might forget about the negative sign altogether. So the magnitude of this component will be capital T, and there will be 0 x component. So we've been using this rule to break those into components. Notice, as usual, that your plus or minus signs depend on your axes. So make sure you have clearly written down your axes so that you can use those axes to get the correct plus or minus signs for your components. Now let's deal with the weight forces. We use these special formulas to calculate the magnitudes of the weight forces, remembering that mass 1 is 3 kilograms and mass 2 is 2 kilograms. So we got 29.4 newtons for the magnitude of weight 1 and 19.6 newtons for the magnitude of weight 2. Now we need to break those weight forces into components. I'll start with weight 2. So weight 2 is, parallel to the y-axis. Weight 2 points in our positive y direction. So weight sub 2y will be positive 19.6 newtons. And there will be 0 x component for weight 2 using this rule. Now I was able to use this rule for weight 2 because weight 2 was parallel to our y-axis. But if we look at weight 1 is neither parallel nor anti-parallel to either the x nor the y-axis. The weight 1 vector is at an angle, at a slant, to both the x and the y-axes. So this rule doesn't apply to weight 1. Well, this is the situation where you have to draw a right triangle and use SOHCAHTOA. We'll have to draw a right triangle and use SOHCAHTOA in order to break the weight 1 vector into components. Here is a summary of the process for breaking weight 1 into components. We have to draw this right triangle. We draw the legs parallel or anti-parallel to the x and y axes, following this rule. And to find the directions, where we have the head of the overall vector, we should have the head of a component. And where we have the tail of the overall vector, we should have the tail of a component. So this is the head of this component. After you draw this right triangle, you can extend this line downwards to make a large right triangle, and then you can use geometry to find these two little angles inside the little triangle. In this large triangle that I've outlined, this angle plus this angle has to add up to 90. So this angle is 90 minus 30, which makes it 60 degrees. Now in this smaller right triangle that I've outlined, this angle plus this angle adds up to 90. So this angle must be 90 minus 60. So this angle is 30 degrees. I put an asterisk here to show that I've chosen to focus on this 30-degree angle, which means this side is adjacent to the angle we're focusing on, this side is opposite to the angle we're focusing on, and this side, opposite the 90 degrees, is the hypotenuse. Then we use SOHCAHTOA as our memory aid to correctly set up the sine and cosine equations, and we can solve for our components. The first time I recorded this video, I made a small mistake in the algebra here. Notice that here I correctly crossed out these two numbers to show that these two numbers are canceling, but over here on this side, I forgot. I forgot to cross out this number. I should have crossed out this number to show that these two numbers are canceling as well. We use absolute value signs in our SOHCAHTOA equations to remind ourselves that the SOHCAHTOA equations don't determine the plus or minus signs on the components. We need to determine the plus or minus signs in a separate step. Well, we can see that Wx is pointing in our positive x direction and Wy is pointing in our negative y direction. I went through the process for breaking a vector into components on this type of inclined plane situation. I went into this process in much more detail and more slowly in the previous video series on how to solve basic Newton's second law problems. It should be boringly easy. It should be boringly easy for you to break this vector into components. If it wasn't boringly easy, I suggest that you should go back to that earlier series on basic Newton's second law problems and practice that skill of breaking this type of vector into components. keep in mind that if we leave out this negative sign, we're going to get the whole problem wrong. So make sure you include a plus sign in front of all your positive components, because that will help you to remember this type of crucial negative sign in front of the negative components. So here I have recorded those x and y components for W sub 1 that we just figured out using the right triangle and SOHCAHTOA method. Moving on to this normal force, there's no special formula for this normal force, so we'll just represent that magnitude by a lowercase n. This normal force is pointing in our positive y direction. So we will say n sub y is positive, and its magnitude will be lowercase n, and the x component will be 0. Now we're going back to using this rule for breaking the vectors into components. Now we have to deal with the kinetic friction force, and for that there's a special formula. Here's our special formula. We plug in 0.4 as the value of mu sub k, and we don't know what lowercase n is yet. So the magnitude of this kinetic friction is 0.4 n. The kinetic friction is pointing in the negative x direction. So the x component will be negative, and the magnitude will be 0.4 n for the x component, and the y component will be 0 using this rule. Now we've completed these force tables. If you left out this negative sign, or this negative sign, or this negative sign, and you chose these axes, then you would get the problem wrong. So remember to include a plus sign in front of the positive components to help you remember the negative signs that are so crucial in front of the negative components. So now we've completed our free body diagrams and our force table. Take your time when you're drawing the free body diagrams and draw neat and clear free body diagrams, because if you make a mistake in your free body diagrams, you're going to get the rest of the problem wrong. Take your time when you're drawing the force tables and draw a neat, clean, organized force table, because if you make any mistakes in your force tables, you're going to get the rest of the problem wrong. Don't rush through the free body diagram and the force table, because those are the basis for the rest of your solution. So we have completed this step. We used the idea that the magnitude of the tension force was the same at both ends of the rope. We've also completed this step. Now we move on to the Newton's second law equations. Here are our general Newton's second law equations. I wrote down both an x equation and a y equation for object 1. But notice that object 2 has no forces in the x component. Again, you can see here that all the x components for mass 2 are 0. Since all the x components of the forces are 0 for mass 2, there's no need to write the Newton's second law equation for the x component for object 2. We only need to write the Newton's second law equation for the y component for object 2. Now the sigma symbol tells us to add the individual force components on the left sides of these equations. Here I've added all the components, being careful to include negative signs in front of the negative components. We need to plug in for the masses. Mass 1 is 3 kilograms, mass 2 is 2 kilograms. Now we try to substitute for the acceleration components. Let's look at mass 1. Mass 1 is moving parallel to the incline. Mass 1 has no motion perpendicular to the incline. Mass 1 is moving in the x component. Mass 1 has no motion in the y component. And that means a sub 1y is 0. If an object is motionless in a component, then that component of its acceleration is 0. Now we have to deal with a sub 1x and a sub 2y. The object is moving, object 1 is moving in the x component, object 2 is moving in the y component. There's no reason to think that those accelerations are 0. So let's try to figure out what we could substitute for a sub 1x and a sub 2y. Well, let's start by supposing that the masses are speeding up. Notice that if one of these masses is speeding up, the other one has to also be speeding up because they're connected by the rope. In order for them to stay connected by the rope, if one mass speeds up, the other one will have to speed up as well. Well, if the masses are speeding up, that would tell us that the acceleration vectors should be parallel to the velocity vectors. If the masses are speeding up, then according to this rule, the each acceleration vector should be parallel to the corresponding velocity vector. And then now we can figure out the signs of the components. So in this case, a sub 1 would be pointing in the positive x direction. And a sub 2 would be pointing in the positive y direction. As usual, we figure out the sign of the components before we figure out the magnitude. Now, because they're connected by the rope, we do expect both these objects to have the same magnitude of acceleration. So I can use the symbol lowercase a for the magnitude of the acceleration for object 1, and I can use the same symbol lowercase a for the magnitude of the acceleration of object 2. Well, so far our analysis looks pretty much the same as the analysis we used on the previous two problems in this video series. We've obtained plus a for both of these components. But the analysis in this problem is a little bit more complicated because on this problem, we actually don't know for sure that the masses are speeding up. Based on the way that this problem was worded, it's theoretically possible in this problem that actually both masses could be slowing down. In our previous problems, we knew for sure that the masses were speeding up because they were starting from rest. But this problem doesn't say that the objects are starting from rest. So in this problem, it's theoretically possible that the masses could be slowing down. Now, to tell you the truth, it's not very likely that the professor would actually set up this particular type of problem so that the objects were slowing down. For this particular type of problem, where we have objects connected by a rope, the professor probably has set it up so that the objects are speeding up. So it would probably be safe just to plug in plus a for both of the components in your Newton's second law equations. That would give you the right answer. That would give you the right answer for this problem, and it's pretty safe because professors would rarely set up this particular type of problem so that the objects were slowing down. But for the sake of accuracy, and completeness, let's think about what the situation would be like if the masses were slowing down. Over here, we worked out the analysis if the masses are speeding up. Over here, let's work out the analysis if the masses are slowing down. And again, because they're connected by the rope, if one of the masses is slowing down, we would expect that the other one would be slowing down as well. It is possible that they're slowing down. The masses could be slowing down if there's a lot of friction. If there's a lot of friction on mass 1, there could be enough friction to slow down mass 1, slow down the motion of mass 1, which would also slow down the motion of mass 2 because they're connected by a rope. Well, if the masses are slowing down, then we would use this rule. When an object is slowing down, the acceleration vector is anti-parallel to the velocity. According to this rule, if the masses are slowing down, then each acceleration vector should be anti-parallel to the corresponding velocity vector. Then in that case, the acceleration for object 1 would be pointing in the negative x direction, and the acceleration for object 2 would be pointing up, which is our negative y direction for object 2. So if the masses were slowing down, both accelerations would be negative. Now, because they're connected by the rope, they would still have the same magnitude of acceleration. So we can still use the symbol a for the magnitude of the acceleration of object 1, and we can still use the same symbol a for the magnitude of the acceleration of object 2. Now remember that our goal is to get something definite that we can substitute into our Newton's second law equations. Well, if there's two different cases, how do we know what to substitute into our Newton's second law equations? We'd like to come up with some type of equation that applies to both cases. What can we say that's true of both cases so we have a single thing to plug into our Newton's second law equations? Well, the one thing that we can say is true in both cases is that a sub 1x will be equal to a sub 2y. If the masses are speeding up, then a sub 1x and a sub 2y are both equal to plus a. They're equal. But if the masses are slowing down, then the components are still equal. Now both components are equal to negative a, but they're both equal to each other. So here's how we can summarize both cases. Here's a single equation that will be true no matter what. A single equation that will be true no matter what, and this is all that we'll need to help us substitute into our Newton's second law equations. So on this problem, I'm not going to make this substitution. I'm not going to make this substitution because technically we can't be sure so far that the masses are speeding up. Instead, on this problem, I'm going to make this substitution. This is the one substitution that we know would be true, regardless of whether the masses are speeding up or slowing down. By the way, notice that the only reason that these components are equal is because we chose the directions of motion as our positive directions. If we had chosen up as the positive direction for object 2, then this component would be negative and this component would be positive, and then the analysis would be more complicated. Then the analysis would be a little bit more complicated, and then we would have to say that a1x is equal to negative a2y. Well, that's a little bit more complicated because that introduces an extra negative sign. So as usual, we're seeing that we make our life easier on this type of problem by choosing the direction of motion as the positive direction. It's because we chose the direction of motion as the positive direction that these components both came out to not only have the same magnitudes, but also have the same signs. And that allows us to use this simple equation, a sub 1x equals a sub 2y. So this is what I'm going to substitute into my Newton's second law equations. So based on that analysis, we can say that for this problem, we have not only the three Newton's second law equations, but we also have this fourth, very simple equation that we're also going to be using to help us solve the math for this problem. So for a sub 1x, I'm just going to continue to write a sub 1x. But for a sub 2y, I'm going to use this equation and make a substitution. For a sub 2y, I'm going to substitute in a sub 1x, because we just figured out that a sub 1x will be exactly equal to a sub 2y. So for a sub 2y, I'm going to substitute a sub 1x. Why is that helpful? That's helpful because it reduces the total number of variables. Anything that you can do that reduces the total number of variables that you're dealing with makes it easier to solve the math. So now, rather than dealing with the two variables a sub 1x and a sub 2y, now we're just dealing with the one variable a sub 1x. In addition to that, we're also dealing with capital T and lowercase n. So we've used this equation to make a substitution and reduce our total number of variables. Now I've made some simplifications. Adding a negative is the same as subtracting. I took advantage of the 0, and here again, adding a negative is the same as subtracting. We completed this step. Notice how we're trying to organize all the versions of each equation in these adjacent columns. We've also completed this step. We used the rule that the magnitude of the acceleration will be the same for both objects because they're connected by the ropes. We also used this rule. Object 1 was motionless in the y component, so the y component of the acceleration for object 1 was 0. Now it's time to use algebra to solve. This equation so far has 3 unknowns. This equation has 2 unknowns. This middle equation here has only 1 unknown, so let's solve this equation for little n. Here's our result. Little n is 25.5 newtons. Check if that makes sense. Does the sign of this result make sense? This result mathematically came out positive. That makes sense because remember, little n does not stand for the normal force. Little n written without an arrow on top stands for the magnitude of the normal force. A magnitude can never be negative, so it makes sense that this result came out to be positive. Does the size of this result make sense? Well, mass 1 should be motionless in the y component. Mass 1 should have no motion in the y component, but W sub 1y is trying to drag the mass into the surface of the incline. The y component of the weight for object 1 is trying to drag mass 1 into the surface of the incline. To prevent that from happening, the normal force is going to have to cancel out this y component. So for the normal force to cancel out this y component, the normal force will have to equal the y component in magnitude, and it does. We've found that the magnitude of the y component of the weight for object 1 is 25.5 newtons. So it makes good sense that the magnitude of the normal force is equal to the magnitude of the y component of the weight for object 1, because the normal force has to cancel the y component of the weight for object 1 in order to prevent the object from beginning to be dragged through the surface of the incline. I've tried to make that clearer here in this new version of the free body diagram. Notice that in this version of the free body diagram, I've broken the weight force into components to make the analysis simpler. Earlier, we decided that W sub 1x points down the incline and W sub 1y points perpendicular to and into the incline. So in this new version of the free body diagram, I've drawn W sub 1x pointing down the incline and W sub 1y pointing perpendicular to and into the incline. And that should make it clear that it makes good sense that the normal force has to equal the magnitude of W sub 1y in magnitude in order for those things to cancel. Notice that here I've used absolute value signs because I want to focus on the magnitude of this component. It's the magnitudes that have to be equal for the normal force to cancel the y component of the weight. So yes, this result does make sense. Now let's take this result for little n and substitute it into this equation. I've substituted this result into this equation. Now we can do a calculation to simplify. 14.7 minus 0.4 times 25.5. So that will give us 4.5 plus t equals 3a1x. So this equation has two unknowns left. This equation also has two unknowns left. Now, if we consider this equation together with this equation as a system of simultaneous equations, these two equations together form a system with two equations and two unknowns. The two unknowns in the equations are capital T and a1x. Now we can see the value of having made this substitution. By making this substitution, we got rid of this third variable. We got rid of the a sub 2y and replaced it with a sub 1x. And now that allows us to say we have a system of two equations in only two unknowns. Well, that's when we're ready to solve the system. When we have two equations in only two unknowns, we can solve for the unknowns. As on the previous problems in this series, you could just add these two equations. You could use the addition method, and that gives you a pretty quick solution. So let's do that. Let's use the addition method to solve this system of equations. First, let's take this equation and recopy it in this column. I took this equation and recopied it in this column. Of course, if you prefer, you could take this equation and recopy it in this column. Now we're going to use the addition method and add these two equations. Add the two equations. So we do the calculation 19.6 plus 4.5, 24.1, Now we do the calculation negative t plus t, which comes to 0. So these two terms cancel. And that's the reason that the addition method is an especially good method in this situation. The addition method works very well for these equations because the equations are already in a form such that the t terms will cancel when we add the two equations. If these two equations were not already in a form such that the t terms were ready to cancel when we add the equations, then the addition method would work less well, or it might not work at all, and in that case we might be better off using the substitution method. But here the addition method works well, so let's continue with that. Again, the t terms have canceled, so here we simply have 2a sub 1x plus 3a sub 1x, which comes to 5. A sub 1x. Now we solve this equation for a sub 1x by dividing both sides of the equation by 5. 24.1 divided by 5 is 4.82. So we get a sub 1x equals 4.82. Remember to put the units in meters per second squared. We have figured out the value for a sub 1x, and now that immediately also tells us the value for a sub 2y. We know that a sub 2y is equal to a sub 1x, so a sub 2y is also equal to 4.82 meters per second squared. Now, if we want to, we can use this result for a sub 1x to determine a value for capital T. Do we care what the value of capital T is for this problem? Well, yes, remember that capital T is one of the things that the question was asking us for, so we certainly do care about the value of capital T for this problem. So how exactly do we use this result to find capital T? Well, we have a choice. If we like, we can take this result and substitute it into this equation and then solve for capital T. Or, alternatively, if we like, we could take this result and substitute it into this equation and then solve this equation for capital T. So we can either substitute into the Newton's second law x equation for object 1, or we could substitute into the Newton's second law y equation for object 2, whichever you like. Well, this equation will be slightly easier to work with because this equation involves plus t. This equation is slightly more difficult to work with because it involves minus t. So let's make the decision to substitute into this equation. We've made this substitution. Now we should do the calculation 3 times 4.82, 14.46. 14.46. Now it's easy to solve this equation for capital T. The calculation is 14.46 minus 4.5, which gives us 9.96. 9.96, and be sure to put units on that result. So now we've demonstrated how we could use the addition method to solve the system of two equations and two unknowns that we obtained. Notice that as usual we are arranging our equations in adjacent columns. Using this adjacent column approach helps us to keep the math neat and clean and organized. Remember that the addition method was a good method to use here because the two equations were already in a form such that the t terms would cancel when we added the equations. If the two equations were not already in a form such that the t terms would cancel when you add the equations, then the addition method would work somewhat less well, or perhaps would not work at all, and it might be preferable then to use the substitution method. For completeness, I will now show you what the substitution method would look like for this problem. Now here on the screen is a summary of the substitution method for solving the system of two equations in two unknowns. If you saw this problem on an exam, it would probably be better to use the addition method because for this particular problem, the addition method is simpler and involves fewer steps. but it's important to know about the substitution method because there are some other problems where the addition method works less well or does not work at all. Now, actually, the first time I recorded this video, I used the substitution method to solve the system of equations. So for most of the rest of this video, you will see the substitution method summarized on the screen. But nevertheless, I do think that if you saw this on an exam, it would be preferable to use the addition method for this particular problem. Now let's ask whether our results make sense. Does the sign of this result make sense? Mathematically, a1x came out to be positive, so a2y also came out to be positive. Does that make sense? Well, in our earlier analysis, we determined that if both of the acceleration components were positive, that would be the case where the masses were both speeding up. So since these results came out to be positive, that indicates that the masses are speeding up. As this slides down the hill and as this falls, they'll be speeding up. That certainly makes good sense. It certainly makes good sense that the masses are both speeding up. Now, we mentioned earlier that it would have been theoretically possible if there were a lot of friction for the masses to be slowing down. If the incline has a lot of friction, it would have theoretically been possible for the masses to be slowing down, but it turned out that that was not the case here. It turned out that, in fact, both acceleration components are positive, so in fact, they are both speeding up. As I mentioned earlier, for this type of setup with two objects connected by a rope, professors would usually write this type of question so that the masses would be speeding up. It would be rather unusual, I think, for a professor to write this particular type of setup so that it had an outcome where the masses were both slowing down. We've seen that it's a good idea to put positive signs in front of positive components to make sure that you're actually thinking about the sign separately. So I'll go ahead and put in these plus signs to emphasize that mathematically these two components came out to be positive. Theoretically speaking, it was possible that they could have come out to be negative, but they did come out to be positive, which indicates that both masses are speeding up. How about the magnitude of these acceleration components? Does the number 4.82, is that a reasonable magnitude? Well, notice that 4.82 meters per second squared is less than 9.8 meters per second squared. The acceleration magnitude is less than freefall acceleration. Does that make sense? That does make sense, and we can see why by focusing on mass 2. Mass 2 is falling. Mass 2 is falling, but it's not in free fall because its fall is being held back by tension force 2. So mass 2 is falling under the influence of gravity, the weight, but it's also being held back by the rope. So we would expect it to be falling with a smaller acceleration than free fall acceleration. So it makes good sense that this acceleration is less than free fall acceleration because mass 2 is being held back in its fall by the rope. So yes, it does make sense that the magnitude of this acceleration is less than free fall acceleration. What about this result for capital T? Does this make sense? Does the sign of this result make sense? This result came out to be positive. Does that make sense? Well, remember that we're using capital T without an arrow on top to stand for the magnitude of the tension force. A magnitude can never be negative, so it makes good sense that this magnitude came out to be positive. And how about the size of this result? Does the size of that result make sense? Well, let's focus on mass 2. So we've determined that the tension force being exerted on mass 2 is 9.96 newtons. That's the same tension on both sides of the rope. I guess I can just call this capital T because it's the same tension on both sides of the rope. And earlier we found that the weight for mass 2 was 19.6 newtons. So I wrote down here that the magnitude of the weight for mass 2 is 19.6 newtons. So this tension force came out to be smaller than the weight in magnitude. Does that make sense? Does it make sense that the magnitude of the tension force came out to be smaller than the magnitude of the weight of mass 2. Well, that makes sense because that's consistent with our result that the masses are speeding up. Now we can see why the masses are speeding up. Weight force 2 is pulling down on mass 2, trying to speed it up in its fall. This tension force from the rope is pulling upwards on mass 2, so the tension force is trying to slow it down as it falls. You can see that the weight force is greater than the tension force in magnitude, so the weight force is going to be winning, so to speak, and that explains our result that the masses are speeding up. That explains why the acceleration component came out to be positive, showing that the object was speeding up. So now we can see all these results are consistent with each other. A tension force that's less than the weight of mass 2 in magnitude indicates that the downward force is greater than the upward force on mass 2, and that indicates that mass 2 really will be speeding up as it falls, and that's consistent with our positive acceleration component for mass 2, which also indicated that the mass should be speeding up. Notice that in this version of the free body diagram, I tried to draw the weight 2 arrow longer than the tension arrow to show that weight 2 has a greater magnitude than the tension force. That explains why we ended up with the result that the mass was speeding up as it's falling. These results are all consistent with each other, and they do make sense. Now we found the x component of the acceleration for mass 1, and we found the y component of the acceleration for mass 2. But we are interpreting the question to be asking us for the magnitude and direction of the overall acceleration vectors for both masses. So let's take this information about the acceleration components and translate it into information about the overall acceleration vectors. We want to use what we know about the components of the acceleration vectors to figure out information about the overall acceleration vectors. Well, we know the value for a1x, positive 4.82 meters per second squared. Positive 4.82 meters per second squared. And we also know the value for a2y, positive 4.82 meters per second squared. Now, because mass 1 is motionless in the y component, a sub 1y is 0. We already used that idea when we substituted 0 for a sub 1y in this equation. And furthermore, because mass 2 is motionless in the x component, a sub 2x is 0. Well, that makes it easy to use these components to find the overall vectors. If one component of a vector is 0, then the magnitude and direction of the overall vector is the same as the magnitude and direction of the non-zero component. So the magnitude of a sub 1 is the same as this magnitude, 4.82 meters per second squared. And the direction of a sub 1 is the same as the direction of this component. This component points in the positive x direction for mass 1. The positive x direction for mass 1 is parallel to and down the incline. So the direction of the overall acceleration for mass 1 is parallel to and down the incline. Remember that when we write this symbol without an arrow on top, it stands just for the magnitude of this overall vector. Here I included the arrow on top because this symbol stands for the complete vector, including its direction. Now we can apply the same idea for A2. A2, the overall vector for A2 should have the same magnitude as this component, 4.82 meters per second squared. And the direction of the overall vector is the same as the direction of this component. This component points in the positive y direction for mass 2. The positive y direction for mass 2 points down, so the direction of the overall acceleration for mass 2 is straight down. Remember that when we write components by themselves, we include plus signs in front of positive components because a component could be either positive or negative. On the other hand, when I write magnitudes, when I write these magnitudes, I don't include plus signs. A magnitude could never be negative, so there's no need to emphasize that these magnitudes are positive. Now we use this information about the overall vectors to answer the question. We are interpreting the question to be asking us for the magnitude of the tension. We figure that out from our algebra, and I've rounded that number off to 10 newtons in my answer. And we're interpreting the question to be asking for the magnitude and direction of the overall acceleration vectors for mass 1 and mass 2. So here we worked that out, and here I've put that in the answer to the question. Notice that I also drew the acceleration vectors here in the picture to emphasize that the direction of the acceleration for mass 1 is parallel to and down the incline, and the direction of the acceleration for mass 2 is straight down. This is actually maybe a more complete and comprehensive answer than the professor would require for full credit on this problem. The professor might be satisfied just to see that you've gotten this results from your algebra. If the professor can see that you've gotten, if you just identify these results from your algebra as the answer, the professor might be satisfied with those answers. Since the y component of a sub 1 is 0, and since the x component of a sub 2 is 0, the professor might be satisfied if you just find these two components and use those as your answers for the accelerations of the masses. So we completed this step. We want to make our checks on our answer, check that you answered the right question and that you answered all parts of the question. So the question was asking about the tension and the acceleration, and we answered that. Notice how important it is to answer all parts of the question. Some students might only figure out the acceleration and forget the tension, or some people might figure out the tension and forget the acceleration. So make sure that you've answered all parts of the question. We've made some checks that our answer makes sense. Make sure that you include units. So we included the units on both the tension force and the acceleration. And this check is not relevant for a numeric problem. Now let's do a recap of our solution for this problem. Here, summarized on the screen, is a summary of some of the key steps in our solution for the problem. On the screen right now, I have illustrated the addition method for solving the system of equations. The addition method involved taking this equation, recopying the equation over here, and then adding the two equations. The addition method worked well because these two equations were already written in a form such that the t variables will cancel out when we add the two equations. Then we were able to solve this equation for a sub 1x, which also told us a sub 2y. Then we took this result and substituted it back into this equation in order to solve for capital T. Remember, if the equations were not already written in a form such that the t variables are ready to cancel when we add the two equations, then the addition method would work less well, and in that case it might be preferable to use the substitution method. The first time I recorded the video, I did use the substitution method, so for the rest of this recap, you will see the substitution method for solving the system of equations illustrated on the screen. So in this problem, we handled the acceleration a little bit differently than we did in the previous problems. So in this problem, the way we handled the acceleration was by saying that a1x equals a2y, and we used that to substitute a1x in for a2y, and that allowed us to reduce the number of variables so that we ended up with a system of two equations and two unknowns that we could solve simultaneously. Here again is the thought process we went through to assure ourselves that a1x will definitely equal a2y. It's possible that both masses are speeding up, and we saw that if that was the case, then a1x would equal a2y. It's theoretically possible for this setup that both masses could be slowing down, but we saw that still in that case, a1x would still equal a2y. And again, notice that the reason a1x equals a2y is because we chose down as our positive direction for mass 2. If we had chosen up as the positive direction for mass 2, our life would be more difficult, and then a1x would equal negative a2y, which is a more difficult equation to come up with. So as usual, you'll make your life easier if you choose the direction of motion as the positive direction for both of the objects. So we handled acceleration a little bit differently on this problem than we did on the two previous problems. For the two previous problems, we just made substitutions that looked like this. On the previous problems, we just made substitutions that looked like this, because on the previous problems, we knew for sure that the masses were speeding up because they started from rest. If an object starts from rest and then begins moving, the only way that could happen is if the mass was speeding up. So on the previous problems, we knew for sure that the masses were speeding up, and we could just substitute plus a for the acceleration components. On this problem, the objects are not necessarily starting from rest, and therefore it was theoretically possible that they could be slowing down. So on this problem, to be technically accurate, the best way to be technically accurate was to make this substitution, a1x equals a2y. Another aspect of this problem that I don't think we've seen in the previous couple of problems in this series is that this was a problem where you had to use a right triangle and SOHCAHTOA to break one of the forces into components. We needed SOHCAHTOA to break weight force 1 into components. So here again is the summary of the method that we used for breaking weight force 1 into components. Again, it should be boringly easy for you to break this weight force into components. If it's not boringly easy, you need to practice this method until it is boringly easy. Remember that you can get more detailed practice with breaking this type of vector into components from my earlier series on basic Newton's second law problems. And I also have another video series that's devoted just to the techniques for how to break vectors into components. So make sure that you get to the point where it's boringly easy for you to break vectors into components. That's a crucial skill for doing well on your exams. Remember that a crucial part of breaking the vector into components is getting the correct negative signs when you need them in the components. Notice that when I draw this right triangle, I don't draw this right triangle in my main sketch or in my free body diagram. I draw a separate picture for this right triangle that I'm going to use to break this into components. I don't try to break the weight force into components in the main free body diagram. That would make this diagram too messy. Instead, we started a separate sketch for breaking weight force 1 into components. Remember that if you can find enough room on your page, it's convenient to organize the math in adjacent columns. By organizing the math in adjacent columns, I think that helped us to stay organized and avoid getting confused. Of course, this problem continued to illustrate the importance of the axes for when you are dealing with these types of problems, and we saw that it's fine to choose different axes for the two objects. For this particular problem, it is particularly important to choose different axes for the two objects. This particular problem would be far more difficult if we tried to use the same axes for both objects. It's much better on this problem to choose different axes for the two objects so that we could handle one object that was falling straight down and another object that was sliding at an angle down the incline. What is the most common mistake made by physics students? Well, I would say that the most common mistake made by physics students is confusing the concepts, mixing up the concepts. On a problem like this, you have to work hard not to mix up the concepts with each other. For example, it's very important not to mix up or confuse weight 1 and weight 2. For example, weight 1 has to be broken into components using SOHCAHTOA, but we don't need SOHCAHTOA for weight 2. Here's another example. It's very important not to confuse a sub 1y with a sub 2y. Notice how a sub 1y was 0, but a sub 2y was not 0. It was very important not to confuse the tension force exerted on object 1 with the tension force exerted on object 2. Both of those tension forces had the same magnitude, but notice that the pattern of their components was quite different. They had quite different patterns of components, and in order to get those components correct, we have to be careful not to be mixing up those two tension forces in our minds. Don't confuse or mix up the concepts. How do you make sure that you're not mixing up the concepts? Well, one important technique is always try to use the exact right symbols, including the exact right subscripts. We use the 1 and 2 subscripts to avoid confusing weight 1 and weight 2. And again, we use the 1 and 2 subscripts to avoid confusing tension 1 and tension 2. And 1 and 2 subscripts to avoid confusing A sub 1y and A sub 2y. Another very important technique is think in terms of components. For example, it's very important not to confuse or mix up A sub 1x and A sub 1y. Notice how A sub 1y is 0, but A sub 1x certainly is not 0. So again, we have to use the correct x and y subscripts and think in terms of components to make sure we're not mixing up those two components. Notice how we were very clear in our thinking that we were focusing on the x component of the acceleration for object 1, but focusing on the y component of the acceleration for object 2. Here's maybe the most important piece of advice for not mixing up the concepts. Don't use the word it. Don't say it's 29.4 newtons or it's 19.6 newtons. Instead, always label each concept with the correct name or symbol. Say that the magnitude of the weight for object 1 is 29.4 newtons, or say W sub 2 is 19.6 newtons. Don't say it is positive t or it is 0. Say t sub 1x is positive t and t sub 2x is 0. Don't say it is 0 or it is equal to a sub 1x. Say that a sub 1y equals 0 and a sub 2y equals a sub 1x. Don't use the word it. Instead, label each concept that you're thinking about with the correct name or symbol. Don't say it is n. Say the magnitude of the normal force is n. Don't say it is 0.4 n. Say the magnitude of the kinetic friction force is 0.4 n. If you make a strong effort not to use the word it, but always to label what you're thinking about with the correct word or symbol, that will give you a powerful technique to help make sure that you're not mixing up and confusing the concepts. This is important advice both when you're talking about a physics problem, but also just when you're thinking about it in your head. Even when you're just thinking through the problem in your head, try to avoid using the word it in your own thoughts. Label each concept with a name or a symbol, even when you're just thinking about them in your thoughts. That's a technique that I try to model during the videos. During the videos, I try to avoid using the word it, and instead I try to always label exactly which concept I'm thinking about with the correct name or symbol. And I would encourage you to try to imitate that habit in your own thinking about physics. One of the most common mistakes that students make in their physics course is mixing up and confusing the concepts. And if you use these 3 techniques, these will give you some powerful habits to help you avoid mixing up and confusing the concepts. Here's one more simple example. Don't confuse weight and mass. Mass is a scalar which has SI units of kilograms. Weight is a vector which has both a magnitude, which we figured out here, and a direction, which we put in our free body diagram. That's just one more example of the importance of not mixing up and confusing different concepts. So don't say that it is 2 kilograms or it is 19.6 newtons. Instead say mass 2 is 2 kilograms and the magnitude of weight 2 is 19.6 newtons. By labeling the concepts, you are less likely to mix them up with each other. Here's one more example. Don't mix up the concept represented by this symbol and the concept that is represented by this symbol. This symbol, mu sub k, stands for the coefficient of kinetic friction, which is a scalar and which has no units. This symbol stands for the force of kinetic friction, which is a vector, which has both a magnitude, determined by this equation, and a direction represented in the free body diagram. And of course, that force of kinetic friction has SI units of newtons. So don't say that it is 0.4 or that it is 0.4 n. Instead, say that mu sub k is 0.4, or the coefficient of kinetic friction is 0.4. And say that the magnitude of the force of kinetic friction is 0.4 n, or F sub k is 0.4 n. Don't confuse the coefficient of kinetic friction with the force of kinetic friction. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.